We've seen that our vector function f of t equals x of ti plus y of tj equal cosine of pi ti plus t squared j has a graph that follows this path and can be defined by a series of vectors for different values of t that are rooted at the origin and follow this path as we move along. In order to understand the properties of this vector function, it's going to help if we understand the properties of its derivative and its magnitude. Now, the vector function, again, let's just take another quick look at our vector function. It's cosine pi ti plus t squared j. What would the derivative with respect to t of our vector function be? Well, the simplest and most logical answer is it would be the derivative of cosine pi t multiplied by I plus the derivative of t squared multiplied by j. After all, I and j are constant vectors. Taking a derivative, it turns out we can treat them simply as constants with respect to differentiation. So the only thing we have to differentiate is the cosine of pi t and t squared. We have the rules of differentiation, constant multiple, sum, and so forth. And if we just use those rules, we find that the derivative of our function is, well, the derivative of the cosine of pi t is negative pi sine of pi t. The derivative of t squared is 2t. And we might want to make just a little note of that, maybe up here in the corner. Cosine of pi t prime, since I don't have a lot of room to write dt, is just negative pi times the sine of pi t. And the derivative of t squared is 2t. You should be familiar with the derivatives at this point and should have no trouble understanding that these are the derivatives of the x and y components. So, for example, f prime of 1 is just 2j. If we write down the function f prime of 1, substitute 1 for t, we're going to find that we have the sine of pi, which is 0, so there's no I component, and 2 times 1 for j, which just gives us 2 times j. F prime of pi, 3 pi over 2 similarly can be evaluated by plugging 3 pi over 2 into this expression, and we get pi I plus 3j. Now let's see what that might mean in terms of the graph of the function, because if we consider, especially let's consider the meaning of f prime of 1. Okay, we found that to be 2j. Now if we're following this vector along, if we're following this path, then at t equals 1, of course here's our t equals 1 point, and that will correspond to this vector right here. How is our direction of motion, and how's our direction of motion changing? Well, at this point, if we're riding along a roller coaster, let's say, at this point we feel like we're moving forward. Now if we see how the roller coaster is turning, we see that we're going to shortly be moving to the right. But at this point we're moving forward, and we have a velocity which could be represented by the length of this vector. It turns out that this vector, f prime of 1, is 2j. When t represents time, then the derivative of this vector function represents the magnitude and direction of our motion, of our velocity. Okay, so at this point we're moving in the direction of 2j, and the speed of our motion will have magnitude 2. Now we haven't specified what units, what our units of length are, or what our units of time are, but whatever they are, the magnitude of this vector would represent velocity of 2 units of length per unit of time, and let's not digress too much into that idea. Okay. The idea here, though, is that f prime of 1 certainly is compatible with the idea that this is 2j. The vector would be vertical, and that's exactly what we would expect at that point. When we get up to the point 3/2, well, at 3/2, remember the point is here, so we're going to be at this point on our graph, and if we draw a vector in the direction of our motion, f prime of 3/2 is pi I plus 3j. So this vector might be pi I plus 3j. Now that would actually make it a little bit longer than I've drawn it. If this vector has magnitude 2, this vector would have magnitude around 4.5, so it would be quite a bit longer than I've drawn it, so it's not really to scale, but we get the idea. If we draw the vector pi I plus 3j at this point, that's going to give us not only the direction of our motion at this instant, but how fast we're moving. Another important quantity is the magnitude of our vector, and the magnitude of a vector is just found by the Pythagorean theorem. If x and y are our components, if x of t and y of t are our components at a certain instant, then the magnitude of this vector is going to be the square root of x squared of t plus y squared of t. Again, simply an application of the Pythagorean theorem. For our particular function, x of t is a cosine of pi t, y of t is t squared, so if we plug those in and simplify, we end up with the fact that magnitude of f of t is cosine squared of pi t plus t to the fourth. Square root of the quantity, cosine squared pi t plus t to the fourth. To make a couple of notes about this magnitude. In the first place, the magnitude of the cosine squared of pi t never exceeds 1 because the cosine can't exceed 1. T to the fourth, on the other hand, is unbounded. It can get as big as you like. And we could conclude a lot of things about the properties of this function. One thing we could conclude is that if t is very large, then since the cosine squared is never bigger than 1, if t gets big enough, the cosine doesn't really contribute very much to the magnitude, and the magnitude of the vector is going to be close to t squared. We can ask questions like, at what rate is the magnitude of this vector changing? At what rate is the length of the f of t vector changing at any instant? And we would answer that by analyzing this function.